Okay, hello everybody. I'm back. I'm gonna show you guys what happened. Okay, so EDF Mark 9. This EDF right here, what happened to it? So, we had a thicker fan diameter. So, the fan grew from 20 millimeters in thickness to 40 millimeters in thickness, giving the fan blades more surface area, which means basically means more air that I'm going to be pulling in. Hopefully, that's my theoretical idea here. Then, so that basically allowed the motor to pull in more, draw in more air, which gives us better thrust output. Then, the second stator stage, basically because the second stator stage is made up of airfoils, right? That's an airfoil right there. Basically, what that did was that created more lower pressure zones on the inside of the EDF, and I think that would create less stress on the motor, pretty much, just less resistance because there's less air inside the EDF because all of the air is being funneled out at a faster speed because we're generating more thrust with these lower pressure zones that are created with these stator stages. Then my vibration dampening technology, where we have the TPU and the TPE for the vibration dampeners right here, beautiful work. They worked so well, in fact. I remember I didn't feel any vibrations in my hand. Like, it was really smooth. Next. And actually, yeah, that's pretty much it, actually. All of those things combined together allowed for more energy to be going to the motor. So there's less energy on the vortices because of the gutter inside of the motor design, and this halo stops the vortices from being created at the tips of the motor. So that gives everything more energy to be used. So that allows the motor to spin closer to its rated 39,000 RPMs. And that could explain why it exploded on me when I made it out of PETG, because PETG has a very low, well, not very low, but PETG has a low tensile strength, which is a material's ability to be pulled apart. And that is why it exploded.